Okay, this is feedback for question 1 on the How Fast homework. So this is a reaction between hydrogen and nitrogen monoxide. You're given a rate equation and the data. You're asked to calculate the rate constant K, which is in that rate equation. So we're going to have to rearrange that rate equation for K. So we need to get rid of these two terms. So if we divide by those terms, we can then cancel those out, but whatever you do to one side, you must do to the other to make it fair. So now we've got our rearranged equation for K. Okay, we can now substitute our values in. So using that button, our rate is 4.5 times 10 to the minus 3. Then move the cursor down. We're going to have 6 times 10 to the minus 3 for our hydrogen, multiplied by 3 times 10 to the minus 3 for the nitrogen monoxide, but we must make sure that's squared. So that gives us our final answer here. 833.33333. Okay, so there's our answer, but we need to check, how do they want the answer given? Well, they're asking for an appropriate number of significant figures. So we need to look back at the data in the question to find the data provided to the least number of sig figs. So here it was 3, here is 3, and here is 2. So we need to give our answer to 2 sig figs, which means that 8 is significant, 3 is, but the rest aren't. So it's going to be 8, 3. Now we do need to replace these with zeros because we need to remember that this is 83,000. So 83,000 would be correct to 2 significant figures. That 3 there, because it was lower than 5, meant that we kept that value as a 3. We rounded down effectively. You could have given that in standard form, so if we move the decimal place, that would give 8.3 times 10 to the 4. We'd move that 4 times. Okay, so there's your correct answer there. So looking, we've got 2 marks so far. 1 for the working out, including the rearranged equation, and then the second mark for the answer to 2 significant figures. The third mark then comes from the units. So we've got the rate at the top, mole per decameter cube per second, and then the concentrations underneath. So concentration of the hydrogen, and then the concentration of the nitrogen monoxide, but that's squared. Okay, so then we can cancel those out, which means that we've got second to the minus 1 over, well, let's get rid of that bracket. So we have mole to the 2 and dm to the minus 6. And then we want to bring that up to the top, so we're going to invert those powers. So mole to the minus 2, dm to the 6, and second to the minus 1. If we're really fussy, we'd put that dm to the 6 first, because it's the positive one, and then we go alphabetical order. But to be honest, it doesn't really matter. You'll get the mark either way. Okay, so there's your third mark. All right then, so let's have a look next. It's saying predict what would happen to the rate if we change the concentrations. So if H2 is doubled, well, we know that rate is proportional to the concentration of hydrogen raised to its respective power. So we know that that's to the power 1. So if we're saying we're going to double that, let's say that's 2, then because it's the reaction is first order with respect to that concentration, it's going to be directly proportional. So the rate would also double. Okay. Let's have a look at nitrogen monoxide now. So if nitrogen monoxide was halved, so we know that the rate is proportional to the concentration of NO raised to the power of 2, because it's second order, the reaction is second order with respect to NO. Then if this is going to be times by halved, so 0.5, then really that's what we're working out. If we've got 0.5 raised to the power of 2, then that's going to be 1/4 or 0.25, the effect. There you go. So that's because the reaction is second order with respect to the nitrogen monoxide. Okay, if H2 and NO are both tripled, so the rate is proportional to, so if we triple the H2, that's raised to the power of 1, and we multiply that by the nitrogen monoxide, which is tripled, but that's to the power 2, then effectively what we're doing here is 3 times 3 squared, which is 27. So the rate will actually go 27 times as fast. Okay, and it's showing that working out there. Okay. The overall equation then now, so we're going to be looking at a mechanism. So the overall equation is 2 hydrogens plus 2 nitrogen monoxides goes to nitrogen and 2 waters. Now you were given, you were asked to come up with a 2-step mechanism. First of all, explain what is meant by the rate determining step. Well, that's a simple definition. It's the slowest step of that mechanism. And you were asked to suggest 2 steps for the reaction and write their equations below. Now, the rate determining step has been partly completed. So they gave you this. And step 2 was given to you like that. Okay, so step 1 and step 2. So step 1 was the rate determining step. So you're basically having to fill in the gaps because those 2 steps combined must make the overall. So we can see here we've already made the 2 moles of water and we've already got the nitrogen. So this species here is going to have to be an intermediate because it doesn't appear in the overall equation. Looking at the left hand side then, this is our rate determining step and we know that that's described from the rate equation. So if we bring back our original rate equation, that tells us that 1 molecule of hydrogen reacts with 2 molecules of NO. So the number 2 here means we'll have to put the NO here and this has to be a hydrogen because this needs to agree with our rate equation. Okay, so if we add step 1 and 2 together, we've got our 2 lots of NO here, but we need another lot of H2. So we're going to have to put that on the second step because we can only have 1 molecule of it here because that has to agree with the rate equation. So really what we're looking for now is an intermediate that effectively will be cancelled out. So looking across at step 1, we've made a H2O, so that's H2 and 1 of those oxygens. That means that we're going to be left with 2 nitrogens and 1 oxygen, so N2O. So that doesn't appear in the overall equation, so we must react that in step 2. And let's have a look if that balances. So H2 plus N2O, does that give us the correct number of atoms for our products? Well, here's our 2 lots of nitrogens there, and then the H2O is made there, so it's balanced. Okay, so 2 marks for that. Okay, so that's the end of question 1.